Just like with the area between two curves, in Cartesian, we can find the area between two polar curves. So, things that we need to know when we are finding the area between two polar curves. We need to know what the graph looks like and which graph is which. We need to know our interval, and we can deal with it in one of two ways. We can deal with it as two integrals that we're just subtracting those areas from each other, or we can look at the fact that we're just taking those two radiuses and subtracting those radiuses squared. So we can kind of look at this in two different ways. So the first thing that we want to do is know what the graphs look like. So we have two functions here. We have 2 plus 2 sine theta and 3 sine theta, and we're looking at them only between pi over 2 and 3 pi over 2. So here's what our graphs look like as a whole. If we were to add in that condition of pi over 2, 3 pi over 2, we want the area between our two curves here. So we want that area between those two kind of slices, almost like the moon. So just like our other ones, we want the bigger radius to be on the outside. So looking at our graph here, our bigger radius is the one farther away from the pole at any point in time from the other equation. And if I'm looking at the outer equation here, this is that 3 sine theta. And I can tell that because 2 plus 2 sine theta, when we look at something like pi, if I'm at pi unit, or pi, theta of pi, 2 times sine of theta, or 2 times sine of pi, is going to be 0. So 2 is our biggest value. So at our angle of pi, 2 would be our piece here. So at -2, 0 on a Cartesian plane, that's where we kind of see that point. So I know that that's where 2 plus 2 sine theta is, and 3 plus sine theta, if I use the same logic, plug in pi, that's going to give us -3, 0 on the Cartesian plane when we're looking at this. So this is our outside function versus this, our inside function. So I would take the bigger sector area if I'm doing it separately first. So 1/2 the integral from pi over 2 to 3 pi over 2 of the outside function 3 plus sine theta squared d theta. And we're going to subtract the inside equation. So 1/2 the integral from pi over 2 to 3 pi over 2 of 2 plus 2 sine theta squared d theta. So this is going to be our equation that we can use to find the area between those two curves. I can simplify it by making it into one integral. They have 1/2 in common, the bounds are in common, so we're really looking at the integral, 1/2 times the integral of 3 pi over 2 times 3 plus sine theta squared minus 2 plus 2 sine theta squared d theta. If we're trying to figure out which one's the outside and which one's the inside, kind of checking some points on our range might be helpful, like checking the endpoints to see if there is a value that kind of gives us a radius that is farther away from one or the other. So I could plug in pi over 2 and pi over 3 to kind of see what happens. When I plug in pi over 2, we're going to get 2 plus 2 times pi over 2, so 2 plus 2 times 1, which is 4, and the other one 3 plus 1, which is 4, gives us the same value, but they shouldn't both give us the same value. If we do, we're just going to pick another point somewhere in those bounds to kind of help us out. So we have two other problems here about area between two polar curves. The first one being the graph of the polar curve r equals 3 and r equals 4 minus 2 sine theta are shown above. The curves intersect at pi over 6 and 5 pi over 6. So the first thing that I would do is label what we have. So even if I don't necessarily know what either of these graphs look like, whenever I see r equals a number, that tells me that it's going to be a circle. So this right here is our r equals 3, and this is our 4 minus 2 sine theta. I also know that our graphs are intersecting at pi over 6 and 5 pi over 6. So right here is going to be pi over 6. Right here is going to be that 5 pi over 6. Let S be the shaded region that is inside the graph of r equals 3 and also inside of the graph of 4 minus 2 sine theta. Find the area of S. So here is kind of the deal of what we're looking at here. We want to know what this area of our circle is. If I look, most of it is still a circle. So if I were to cut off my graph about here and here, this second piece here, this is just the circle that's dealing with this area. The part that gives us trouble is this part. So we're going to kind of have two areas here. We have the area of a circle, and we have that area of our sector. So this is that overlapping area. So our area of a circle, we're just going to use the normal area of a circle equation. The overlapping area that we have on the other side is something that we're going to have to think through. So one of the things that we have to kind of think about is pi over 6 to 5 pi over 6. How much of the circle is that? So if we're looking at pi over 6 to 5 pi over 6, if I were to kind of move that down, so it starts at 0, it starts at pi, we're going to find out that it is a pi over 3, meaning that it's 1/3, or it's going to be 2 pi over 3 distance, so it's going to be 1/3 of our circle. So the rest of the circle is made up of 2/3 of whatever we're dealing with. So when we're looking at our area equation, we want to do 2/3 times pi r squared. R in this case is just the radius of our circle, which is 3. So we have 2/3 pi times 3 squared. We want to add that other area over here, but what I'm going to do is I'm going to go ahead and simplify what we have. So 3 squared is 9. 9 times 2/3, so 9 divided by 3 times 2 is going to be 6. So that area of our circle is made up of 6 pi. So now what we need to do is figure out the area of this other piece. Well, we know we need 1/2 the area of a sector. We know that we're starting at pi over 6 and we're ending at 5 pi over 6. And we need to know what equation that we're dealing with. The nice thing here is that we don't really need to worry about the area between these two curves. We just need to worry about this area that is made up of that other function. So our radius here is going to be that 4 minus 2 sine theta squared. And if I can't simplify it at all, we're going to just leave it as is. Okay, one of the things you may notice is it says calculator active FRQ, which means that they would be expecting you to plug this in and find a singular answer. So we would plug in 6 pi and add this area over here, so 1/2 times the integral of pi over 6, from pi over 6 to 5 pi over 6 of the quantity 4 minus 2 sine of theta all squared d theta. If we do put this all in a calculator, we're going to get 24.708. And that's going to be whatever unit area-wise of our function. So that shaded piece here, all of this is going to be 24.708. We have one more here, which is our last calculator active question. We have the figure above shows a graph of the polar curve, r equals 2 cosine of 3 theta, and r equals 2. What is the sum of the areas of the shaded regions? So we are going to kind of take this as a washer method problem. The big difference being that it's not a volume, but that idea of taking the outside area minus the inside area. So we have the outer area of that circle itself is kind of taking up everything. So this is that r equals 2. This polar rose is that r equals 2 cosine of 3 theta. So we want to take the area of our circle and subtract the area of that polar rose. Well, the area of a circle we know is pi r squared, so we have pi times our radius, which in our case is 2 squared. So we have 4 pi. Now we need to take the polar curves sector area away. You may notice that it doesn't give us bounds, so we kind of have to think through what our bounds would be. 3 theta is going to tell us that we have our petals are happening at every third of the circle. So when we kind of look in our function, I am going to know, based off of graphing these, that we only need between 0 and pi to kind of deal with that. If I do too much extra, I'm going to be subtracting extra area that we may not want to. If I don't do all of it, I might be subtracting not enough area. And because it's calculator active, if I really need to, I can change my calculator to polar mode, which I will show you how to do when I get back, and graph these functions on their own. So we have 0 to pi. I need the 1/2 because I didn't write it already. And our function 2 cosine of 3 theta d theta. And then just like before, it is a calculator active question, so we're going to go ahead and plug this into a calculator to get an answer. And the answer that we get happens to be this 9.425. Like I said, the worst part of polar is those bounds. It gets a little bit better the more that you do it. It just takes practice.